Hi, I'm Alvin. Welcome to FBNetV3. This brief video is titled, What Neural Architecture Search Fails to Search? In case you're wondering if you're in the right place, the paper title is down below in bold. Let's get started. First, I'll say recipe a lot in this video. Recipe just means training hyperparameters, like learning rate. Now, onto the problem statement. Many previous papers observe that changing the neural network architecture changes which training recipe is optimal. We see this all the time. After designing a new neural network, we'll tune the learning rate, weight decay, momentum, etc. So changing the architecture changes the optimal training recipe. The converse is also true. After changing the training recipe, tweaking the learning rate, dropout, etc., the best possible neural network architecture changes. So changing the training recipe changes the optimal architecture, and yet, neural architecture search algorithms use only one training recipe during search. This means that neural architecture search algorithms overlook more accurate architectures. Fortunately, the answer is simple. Perform a joint search over both architectures and recipes at once. However, here's why previous methods haven't already performed joint searches on large-scale datasets like ImageNet. For differentiable neural architecture search, it's impossible to search over training recipes. An alternative is predictor-based search. Here, the predictor accepts architectures as input and predicts the accuracy of that architecture. However, these algorithms take thousands of GPU hours and hundreds of architectures to train already. Further including training recipes in the search space would blow up the search space. The problem is twofold. We need neural architecture recipe search, but with searches already being so expensive, this larger space means prohibitive increases in computational cost. So how do we search this even larger space more efficiently? The insight is to use a predictor-based approach, but to pre-train our predictor on quote-unquote free statistics. Here's how that works. First, consider a neural network. We describe the neural network architecture, encode the architecture, and obtain an architecture embedding. Finally, we use this embedding to predict the architecture's flops and parameters. Here's the kicker. Computing the flop and parameter counts for an architecture is free. This is our pre-training task, and we can generate an infinite number of architectures for this purpose. Finally, we also consider a training recipe as input. Using both the training recipe and the architecture embedding, we finally predict the accuracy. Here, we plot validation samples for our original predictor, mapping actual accuracy to predicted accuracy. The perfect predictor would place all samples on the line y is equal to x. We'd repeat the same plot, but for a predictor with our pre-training strategy. The pre-trained predictor is qualitatively and significantly more accurate, with points more tightly clustered around y is equal to x. Finally, we quantify pre-training's effect on sample efficiency. Here, we plot the predictor's error as we vary the number of training samples. Pre-training reduces the number of training samples needed by up to 50 times. We employ a few other tricks to reduce computational cost. We employ a Huber loss to robustify the predictor against outliers. Stop training when network accuracy is highly rank correlated with the final accuracy. And use the predictor to guide quick evolutionary searches for each resource-constrained setting. We call this neural architecture recipe search. This yields a family of state-of-the-art compact convolutional neural networks called FBNetV3. For example, our FBNetV3s match EfficientNet and ResNest accuracy with 2 and 7 times fewer flops respectively. The takeaway from this video is that predictor pre-training with free architecture statistics improves sample efficiency by up to 50 times. So, employ predictor pre-training with architecture statistics whenever you can. That's it. For details, check out our paper.